So let's look at problem number 6 in our alkyne chemistry, a mystery molecule. And the information we have is that there's a molar mass of 108 grams. There's an attempt to react it with hydrogen using the Lindlar catalyst, but no hydrogen is absorbed. The molecule is then reacted with a normal palladium on charcoal catalyst in hydrogen, and the molecule does absorb this time 1 equivalence of hydrogen gas, and it results in the bicyclo-4,2,0-octane to be produced. Lastly, the hydrocarbon is oxidized with ozone using dimethyl sulfide as a catalyst, and it produces a cyclobutane derivative, and there's a branch on carbon number 1, CH2CH2CHO, an aldehyde branch, and next door on carbon 2 there's just simply an aldehyde branch, CHO, on the molecule. Explain these observations and give a chemical and structural formula. So let's start with the chemical formula based on a mass of 108 grams. Of course, we'd initially divide that 108 mass by 14 because that's the mass for our CH2 units, and that goes into 108 7 times neatly and gives us 10 extra grams of mass. We could then use that 10 extra grams plus 2 more hydrogens to make an extra carbon in the chemical formula. That takes us to a molar mass target of 108. Of course, the original saturated alkane with 8 carbons would have 18 hydrogens, so we've lost 6 hydrogens in our formula, and for every 2 hydrogens lost, that suggests either a pi bond or there's a ring structure of some kind in the molecule. And next piece of information is that the Lindlar catalyst with hydrogen failed to cause any hydrogen to be absorbed, and that's telling us that the molecule does not have an alkyne carbon-to-carbon triple bond. That Lindlar catalyst is specifically for alkynes to be hydrogenated down to the cis alkene, and that is not happening. So the only hydrogenation taking place in the molecule with a normal palladium charcoal catalyst and hydrogen absorbing just 1 equivalence of hydrogen is telling us that there's just 1 carbon-to-carbon double bond in this structure. That would explain 2 of the hydrogens lost from our original saturation point. So the other 4 hydrogens have to be because of 2 ring structures in the molecule. So let's try and form that bicyclo-4,2,0-octane, which is formed after the hydrogenation with the palladium charcoal. If we start at the bridging points, the smallest bridging point, of course, has 0 carbons in between. The next bridging point is 2 carbons long, and that would give us a cyclobutane part. And then the bridge on the other side is 4 carbons long, so that would give us a cyclohexane ring. And then, of course, 8 carbons altogether to give us that octane. So next, we know that ozonolysis of the original compound produced that cyclobutane derivative with the 2 aldehyde branches. Of course, ozonolysis of our alkene in dimethyl sulfide as catalyst breaks through that carbon-to-carbon double bond and oxidizes each carbon on the opened end. So we could produce a mixture of ketones and aldehydes, as this example suggests. Now, of course, we've got some kind of bicyclooctane derivative with a double bond in there somewhere. The fact that the product from this ozonolysis still gives us a cyclobutane means that the double bond must have been somewhere on this 6-carbon chain of the molecule. Double bond here, here, or here for it to open up like that. So that cyclobutane with 1, 2, 3 carbons on one side to get to the aldehyde, and then just 1 carbon for the other branch opening means that the original link in the molecule must have been from carbon 3 to carbon 4, because as we have here, so that must be the position of the carbon to carbon double bond, and it gives us our final answer. C8H12 with a double bond, which explains the hydrogenation with the palladium on charcoal. No triple bonds, which explains no reaction with the palladium on charcoal with the Lindlar catalyst, and fits the chemical formula.